In the center of our galaxy, 26,000 light-years from Earth, something impossible exists. An object so dense that 4 million suns compressed into a region smaller than our solar system would still not match its gravity. Light itself cannot escape once it ventures too close. Space and time swap their roles at the boundary. Inside, the laws of physics as we know them cease to function. This is Sagittarius A*, the supermassive black hole at the heart of the Milky Way, and it is just one of billions scattered throughout the cosmos. If you enjoy exploring the universe's most extreme phenomena, hit that subscribe button. Tonight, we descend into the abyss. Prepare yourselves, the journey into black holes begins now. In 1783, a British clergyman named John Michell sat in his study calculating the properties of light. He knew from Newton's laws that gravity affected all objects with mass, and he wondered whether light itself could be slowed by gravitational attraction. His calculations led him to a startling conclusion. If you compressed enough mass into a small enough volume, the escape velocity from its surface would exceed the speed of light. Any light emitted from such an object would fall back to the surface like a stone thrown upward from Earth. The object would be dark, invisible, detectable only through its gravitational influence on surrounding matter. Michell called these hypothetical objects dark stars, though they bore no resemblance to the shining spheres we see in the night sky. His paper, published in the Philosophical Transactions of the Royal Society, described the first theoretical prediction of what we now call black holes. The idea languished in obscurity for over a century because Newtonian physics could not fully explain such objects, and the technology to detect them did not exist. In 1915, everything changed. Albert Einstein published his general theory of relativity, replacing Newton's instantaneous gravitational force with a geometric description of space-time. Mass and energy curve the fabric of space and time, and objects move along the curves created by this warping. Einstein's field equations described how matter determines geometry and how geometry dictates motion. Within weeks of publication, a German physicist named Karl Schwarzschild was serving on the Russian front during World War I. Despite the horrors surrounding him, Schwarzschild worked through Einstein's equations and found an exact solution for the space-time geometry around a spherical mass. His solution contained a peculiar feature. At a specific radius determined by the object's mass, the mathematical expressions became infinite. Time appeared to stop. Space seemed to fold in on itself. Schwarzschild sent his calculations to Einstein, who was both impressed and disturbed. The solution worked mathematically, but implied something physically absurd. At what became known as the Schwarzschild radius, reality itself seemed to break down. Einstein believed this mathematical singularity indicated a flaw in the solution, not a real physical phenomenon. Nature would never permit such extremes. He was wrong. The Schwarzschild radius defines the event horizon, the boundary beyond which escape becomes impossible. For any given mass, you can calculate this critical distance. For Earth, it is about 9 millimeters. If you could compress our entire planet into a sphere smaller than a marble, it would become a black hole. For the Sun, the Schwarzschild radius is roughly 3 kilometers. Crush all that stellar mass into a ball the size of a small town, and light could not escape its surface. The calculation is straightforward, but the implications are staggering. The formula involves only fundamental constants: the speed of light, the gravitational constant, and the mass of the object. Nothing in the physics prevents such compression from occurring, yet the result violates every intuition we have about how matter should behave. For decades, physicists argued about whether black holes could actually form in nature or whether they remained mathematical curiosities. Some proposed that physical processes would always prevent matter from collapsing past a certain density. Others suggested that new physics would emerge at extreme conditions, creating pressure that would halt the collapse before an event horizon formed. The debate continued through the 1,920 seconds and 30 seconds as astronomers discovered more about stellar evolution. Stars shine by converting hydrogen into helium through nuclear fusion in their cores. This fusion generates outward pressure that balances the inward pull of gravity. But fusion requires fuel, and fuel eventually runs out. What happens when a star exhausts its nuclear reserves? In 1931, a young Indian physicist named Subramanian Chandrasekhar was sailing from India to England to begin graduate studies at Cambridge. During the voyage, he performed calculations exploring what happens to stars after they stop burning. He knew that white dwarf stars, the remnants of stars like our Sun, are supported by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. This creates a pressure that does not depend on temperature, unlike the thermal pressure in normal stars. Chandrasekhar calculated the maximum mass that electron degeneracy pressure could support. His result shocked him. Above 1.4 solar masses, no amount of electron degeneracy pressure could prevent gravitational collapse. A white dwarf more massive than this limit would be crushed by its own gravity. But crushed into what? The implications were clear but disturbing. If a stellar core exceeded the Chandrasekhar limit, it would collapse catastrophically. Nothing in known physics could stop it. When Chandrasekhar presented his findings to the Royal Astronomical Society in 1935, Arthur Eddington, the most prominent astrophysicist of the era, publicly ridiculed the young man's work. Eddington declared that there should be a law of nature preventing such absurd densities. Stars could not simply collapse without limit. Nature must provide some escape mechanism at extreme densities. The ridicule devastated Chandrasekhar, but his mathematics was correct. Years later, he would receive the Nobel Prize for this work, while Eddington's objections would be forgotten. Nature does not care about our intuitions or preferences. The laws of physics operate independently of human comfort. In 1939, Robert Oppenheimer and his student Hartland Snyder published a paper titled On Continued Gravitational Contraction. They used general relativity to follow the collapse of a massive star past the point where electron degeneracy pressure failed. Their calculations showed that once collapse began, nothing could stop it. The star would shrink past its Schwarzschild radius and continue collapsing to infinite density at a mathematical point called a singularity. From the perspective of a distant observer, the collapse would appear to slow as the surface approached the Schwarzschild radius. Light from the star would be increasingly redshifted, appearing dimmer and redder. Asymptotically, the star would seem to freeze at the event horizon, never quite crossing it, though in reality it had already disappeared inside. Time dilation effects near the event horizon created this illusion. From the perspective of someone falling with the collapsing material, the experience would be entirely different. They would cross the event horizon in finite time, noticing nothing special at the boundary. The collapse would continue until tidal forces tore them apart, a process called spaghettification, because objects get stretched into long, thin shapes. This divergence between perspectives, what distant observers see versus what infalling observers experience, lies at the heart of black hole physics and creates paradoxes that physicists still debate today. Oppenheimer and Snyder's paper appeared in September 1939. The same month, Germany invaded Poland and World War II began. Oppenheimer would soon be recruited to lead the Manhattan Project, and black hole physics would remain a theoretical backwater for another 2 decades. The tools needed to detect these objects did not yet exist, and without observational evidence, most astronomers considered them mathematical curiosities rather than astrophysical realities. The breakthrough came from an unexpected direction. In the early 1960 seconds, astronomers began detecting powerful radio sources scattered across the sky. These sources appeared as point-like objects, similar to stars, but their radio emission was far too strong to come from normal stellar processes. When optical telescopes examined their positions, they found faint blue star-like objects. Spectroscopic analysis revealed something astounding. These objects were not stars at all. Their spectra showed emission lines redshifted by enormous amounts, placing them at cosmological distances billions of light-years away. If these quasi-stellar radio sources, or quasars, were truly that distant, they had to be emitting as much energy as hundreds of entire galaxies from regions smaller than our solar system. No known physical process could generate such power from such a small volume. The energy output was absurd by any conventional standard. In 1963, Astronomer Martin Schmidt measured the redshift of the quasar 3C 273, placing it over 2 billion light-years away. Its luminosity exceeded 100 billion suns. The numbers made no sense. Stars produce energy through nuclear fusion at rates limited by their mass and composition. Even if you packed 1 billion stars into a solar system-sized region, they could not produce the observed luminosity. Something else was happening, something far more efficient than fusion. Theoretical physicists began exploring alternatives. In 1964, Edwin Salpeter and Yakov Zeldovich independently proposed that quasars could be powered by matter falling into massive black holes. When gas spirals into a black hole, it forms an accretion disk, a swirling vortex of material orbiting at increasing speeds as it approaches the event horizon. Friction between adjacent layers of the disk converts orbital energy into heat. The inner regions reach temperatures of millions of degrees and radiate brilliantly across the electromagnetic spectrum. The efficiency of this process is staggering. Nuclear fusion converts about 0.7% of mass into energy, according to Einstein's equation E equals mc squared. Accretion onto a black hole can convert up to 10% or even 40% of infalling mass into radiation, depending on the black hole's spin. This makes accretion the most efficient energy generation mechanism in the universe, apart from matter-antimatter annihilation. A black hole consuming a few solar masses per year could easily power a quasar's luminosity. The accretion disk model explained many quasar properties, but it required black holes weighing millions or billions of solar masses to exist at galactic centers. At the time, this seemed almost as implausible as quasars themselves. How could such monsters form? What process could create black holes 1 billion times more massive than the Sun? These questions would drive research for decades, and we still do not have complete answers. What we do know is that supermassive black holes are not rare cosmic oddities. They appear to exist at the center of nearly every large galaxy, including our own. The Milky Way harbors Sagittarius A*, a black hole weighing 4.1 million solar masses. Andromeda, our nearest large galactic neighbor, contains a black hole of similar mass. More distant galaxies host even larger monsters, some exceeding 10 billion solar masses. These objects are fundamental components of galaxy structure, intimately connected to galactic evolution in ways we are still working to understand. The transition from theoretical curiosity to observational reality accelerated in the 1,970 seconds as X-ray astronomy came of age. Black holes themselves emit no light, but matter falling into them radiates intensely before crossing the event horizon. The X-rays from accretion disks can be detected from Earth if we place telescopes above the atmosphere that absorbs these high-energy photons. In 1972, the Uhuru X-ray satellite detected a powerful source in the constellation Cygnus designated Cygnus X1. The source showed rapid variability, flickering on timescales of milliseconds. This rapid variation implied the emitting region must be very small, since light travel time constrains how quickly a source can change brightness. A region 1 light second across, about 300,000 kilometers, cannot vary significantly on timescales shorter than 1 second. The millisecond variations from Cygnus X1 meant the emission came from a region smaller than Earth. Optical observations identified a blue supergiant star at the X-ray source's position. Spectroscopic measurements revealed the star was orbiting an unseen companion with a period of 5.6 days. Using Kepler's laws and the observed orbital motion, astronomers calculated the companion's mass. The invisible object weighed at least 8 solar masses, far too heavy to be a white dwarf or neutron star. Both types of stellar remnants have maximum masses around 2 to 3 suns. Nothing known could be that massive and invisible except a black hole. The evidence was circumstantial but compelling. Stephen Hawking, who had spent years studying black hole physics, bet fellow physicist Kip Thorne that Cygnus X1 was not a black hole. Hawking later explained this was insurance. If Cygnus X1 proved to be a black hole, he would at least have the consolation of winning his scientific bet. If it proved not to be a black hole, losing the bet would compensate for his disappointment. In 1990, as evidence accumulated, Hawking conceded the bet. Cygnus X1 was indeed a black hole, the first stellar mass black hole identified in our galaxy. Since then, dozens more have been discovered through X-ray observations and orbital dynamics. We now know that stellar mass black holes weighing between 5 and 100 solar masses are common throughout the galaxy, with an estimated 100 million scattered among the Milky Way's 400 billion stars. These objects form when massive stars exhaust their nuclear fuel and collapse. The process is violent and spectacular. A star more than 20 times the Sun's mass will burn through its fuel in just a few million years, far faster than the Sun's 10 billion-year lifetime. When fusion stops, the core collapses in a fraction of a second, and the outer layers rebound in a supernova explosion that briefly outshines the entire galaxy. If the collapsing core exceeds about 3 solar masses, not even neutron degeneracy pressure can halt the implosion. The core collapses past its Schwarzschild radius and becomes a black hole. The connection between supernovae and black hole formation was confirmed through observations of supernova remnants, where the expected neutron star was missing, and through detection of black holes in binary systems, where the companion star showed chemical enrichment consistent with supernova ejecta. But stellar collapse explains only the small black holes. The supermassive monsters at galactic centers require different formation mechanisms. A star can only be so massive before radiation pressure during its lifetime tears it apart. The most massive stars top out around 250 solar masses. Even if such a star collapsed completely into a black hole, it would produce an object far too small to explain the billion solar mass behemoths we observe. Building supermassive black holes requires either starting with heavier seeds or growing stellar mass black holes through millions of years of continuous feeding. Both processes face significant challenges. Astrophysicists have proposed several pathways for supermassive black hole formation. Direct collapse of massive gas clouds in the early universe could create black holes weighing 100,000 solar masses or more without going through a stellar phase. Alternatively, the first generation of stars might have been much more massive than modern stars, up to several hundred solar masses, and their collapse would create heavier seed black holes. These seeds could then grow by accreting gas and merging with other black holes over billions of years. The timeline is crucial. We observe quasars powered by billion solar mass black holes when the universe was less than a billion years old. Growing from stellar mass seeds to these monsters in the available time requires nearly continuous feeding at the maximum possible rate, the Eddington limit we discussed earlier. This seems unlikely given that accretion is typically episodic rather than continuous. Gas supplies fluctuate, feedback from the black hole can expel infalling material, and mergers disrupt orderly accretion flows. Most models struggle to produce enough supermassive black holes early enough without invoking somewhat contrived conditions. The discovery of dark stars, as described in the document you provided, offers an alternative pathway that may resolve these timeline problems. Black holes formed by collapsed dark stars could start with millions of solar masses, providing heavy seeds that eliminate the Eddington limit bottleneck. This is an active area of research with competing theories and insufficient data to definitively choose between them. What we can say with confidence is that supermassive black holes exist, they formed early, and they profoundly influence galaxy evolution. The mass of a galaxy's central black hole correlates tightly with properties of the galaxy's bulge. The central concentration of stars, more massive bulges harbor more massive black holes, with the black hole mass typically around 0.1% of the bulge mass. This correlation implies a deep connection between black hole growth and galaxy formation, though the causal mechanism remains debated. Do black holes regulate galaxy growth by ejecting gas that would otherwise form stars? Or do galaxies feed their black holes through processes that also build up the stellar bulge? Understanding these connections requires understanding what happens near black holes, where gravity reaches extreme intensities and space-time itself becomes wildly distorted. General relativity describes gravity as the curvature of space-time caused by mass and energy. In everyday experience, this curvature is gentle. Earth curves space-time slightly, causing objects to fall and planets to orbit, but the deviation from flat Euclidean geometry is small. Near a black hole, curvature becomes severe. Space and time bend dramatically, creating effects that seem impossible from a Newtonian perspective. Consider the event horizon, the boundary at the Schwarzschild radius. Outside this surface, escape is difficult but possible if you have sufficient velocity. Inside the surface, escape becomes impossible regardless of velocity, because all future-directed paths through space-time lead toward the singularity. This is not because the gravitational pull is infinitely strong at the horizon, it is because the geometry of space-time inside the horizon is arranged such that moving away from the singularity would require moving backward in time, which physics does not permit. The event horizon is a one-way membrane in space-time. Cross it moving inward, and you can never return. Information can flow in, but cannot flow out. This property leads to profound consequences for thermodynamics and information theory that we will explore later. For now, focus on the geometric structure. Outside the event horizon, an observer with powerful rockets could hover at a fixed distance from the black hole, fighting against gravity to maintain position. The required acceleration becomes infinite as they approach the horizon. At the horizon itself, staying at fixed position would require accelerating to the speed of light, which is impossible for anything with mass. Just inside the horizon, no amount of acceleration can prevent you from falling toward the singularity. The roles of space and time have exchanged. Outside, you can move freely in space but must move forward in time. Inside, you move inevitably toward the singularity in what used to be a spatial direction. While the radial coordinate behaves like time, the singularity is not a place in space. It is a moment in your future, as unavoidable as next Tuesday. These strange properties arise from solving Einstein's field equations for the geometry around a spherically symmetric mass. The mathematics is unambiguous, though interpretation remains challenging. Does the singularity represent a real physical infinity or a breakdown of our theoretical framework? Most physicists suspect the latter. General relativity is a classical theory that does not incorporate quantum mechanics. At extremely small scales and high densities, quantum effects should become important, modifying the space-time structure. A complete theory of quantum gravity would presumably resolve the singularity, replacing it with some exotic but finite quantum state. We do not yet have such a theory. String theory, loop quantum gravity, and other approaches attempt to merge quantum mechanics with gravity, but none have produced testable predictions that would let us choose between them. The singularity remains mysterious, hidden behind the event horizon where we cannot observe it directly. This observational inaccessibility is enshrined in what physicist Roger Penrose called the cosmic censorship hypothesis. Singularities formed by gravitational collapse are always hidden inside event horizons. Nature does not permit naked singularities, singularities visible to distant observers without an intervening horizon. If cosmic censorship holds, we can never observe the physics at a singularity directly. The universe politely drapes a veil over its most extreme conditions, protecting the rest of space-time from whatever pathologies occur there. Cosmic censorship remains unproven as a general statement, though specific examples of naked singularities have been shown to be unstable or require unphysical conditions. Most physicists believe some form of cosmic censorship is correct, but we lack a rigorous proof. The question connects to deeper issues about the predictability of physics. If naked singularities could exist, the future evolution of space-time would become unpredictable since arbitrary information could emerge from the singularity. Causality and determinism would break down. The possibility troubles physicists enough that significant effort has gone into proving or disproving cosmic censorship in various contexts. Black holes come in different varieties depending on their properties. The Schwarzschild solution describes non-rotating, electrically neutral black holes. Real astrophysical black holes likely carry angular momentum from the rotation of their progenitor stars or accretion disks. In 1963, mathematician Roy Kerr found an exact solution to Einstein's equations for a rotating black hole. The Kerr solution is considerably more complex than Schwarzschild, with additional features arising from the black hole's spin. A rotating black hole drags spacetime around with it, an effect called frame dragging. Close to the event horizon, space-time itself rotates in the direction of the black hole's spin. Objects near the black hole are pulled along with this rotation regardless of their own velocity. This region, where frame dragging becomes extreme, is called the ergosphere. Within the ergosphere, but outside the event horizon, it is impossible to remain stationary relative to distant stars. You must orbit in the direction of rotation, though you can still escape if you have sufficient velocity. The event horizon of a rotating black hole is smaller than the Schwarzschild radius for the same mass, with the reduction depending on the spin rate. For a maximally rotating black hole, the horizon radius is half the Schwarzschild value. This means rotating black holes can pack the same mass into a smaller volume, and the regions near the horizon experience even more extreme gravitational effects. Rotation also affects the singularity structure. In a Schwarzschild black hole, the singularity is a point at the center. In a Kerr black hole, the singularity forms a ring. The mathematics suggests that objects could potentially pass through the ring and emerge into other regions of space-time, possibly even other universes. These solutions are mathematically valid, but probably not physically realized. Small perturbations would likely destabilize such configurations, and quantum effects might eliminate the exotic regions entirely. Nonetheless, the Kerr solution is essential for describing real black holes since rotation is ubiquitous in astrophysics. Stellar mass black holes formed from rotating stars inherit significant angular momentum. Accretion onto black holes tends to spin them up as infalling material carries angular momentum inward. Measurements of X-ray emissions from accretion disks allow astronomers to estimate black hole spins. Many observed black holes rotate at substantial fractions of the maximum possible rate. This rotation affects accretion efficiency. For a non-rotating black hole, the innermost stable circular orbit exists at 3 Schwarzschild radii. Inside this orbit, objects inevitably spiral inward and cross the event horizon. For a maximally rotating black hole with spin aligned to the orbital motion, the innermost stable orbit moves inward to just above the event horizon. This allows matter to orbit closer before plunging in, extracting more gravitational energy and producing more luminous accretion disks. The maximum efficiency for converting mass to energy through accretion is about 6% for non-rotating black holes and up to 42% for maximally rotating holes. Supermassive black holes in galactic centers probably rotate rapidly due to billions of years of accretion from preferentially aligned material. Measuring their spins provides information about their growth history. A black hole that grew primarily through mergers would show different spin characteristics than one that grew through sustained accretion from a coherent disk. These measurements remain challenging but are becoming increasingly precise with modern X-ray observatories. The third property a black hole can possess is electric charge. The Reissner-Nordström solution describes a non-rotating charged black hole, and the Kerr-Newman solution includes both rotation and charge. However, astrophysical black holes are unlikely to carry significant net charge. Any excess charge would rapidly be neutralized by attracting oppositely charged particles from the surrounding environment. The electromagnetic force is so much stronger than gravity that even tiny charge imbalances create enormous forces, and astrophysical plasmas contain ample free charges to screen any net charge on a black hole within milliseconds. This leads to a famous theorem in black hole physics called the no-hair theorem, proved in various forms by Stephen Hawking, Werner Israel, and others in the 1970 seconds. The theorem states that stationary black holes are completely characterized by only 3 externally observable parameters: mass, angular momentum, and electric charge. All other information about the matter that formed the black hole or fell into it is lost. A black hole formed from collapsing hydrogen is identical to a black hole of the same mass, spin, and charge formed from collapsing iron. The black hole has no hair, meaning no additional distinguishing features beyond those 3 numbers. The no-hair theorem has profound implications. It implies that black holes are remarkably simple objects despite their extreme nature. All the complexity of the infalling matter, the quantum states of every particle, the arrangement of atoms and fields, disappears behind the event horizon. The exterior geometry depends only on total mass, total angular momentum, and total charge. This simplicity is mathematically elegant, but raises deep questions about information conservation. In quantum mechanics, information cannot be destroyed. The state of a system at any time uniquely determines its state at all other times, both past and future. But if all information about infalling matter disappears behind the event horizon, never to return, quantum information appears to be destroyed. This contradiction is the black hole information paradox, one of the most important unsolved problems in theoretical physics, connecting gravity, quantum mechanics, and thermodynamics in ways we still do not fully understand. The paradox emerged from Stephen Hawking's work in the 1970 seconds on quantum effects near black holes. Hawking combined quantum field theory with general relativity and discovered that black holes are not entirely black. They emit radiation due to quantum fluctuations near the event horizon, and this radiation carries energy away from the black hole, causing it to slowly evaporate. Hawking's discovery began with a thought experiment about particle creation in curved spacetime. In quantum field theory, empty space is not truly empty. The vacuum contains virtual particles, particle-antiparticle pairs that spontaneously appear and annihilate so quickly that they do not violate energy conservation, thanks to the Heisenberg uncertainty principle. These virtual pairs normally exist for infinitesimal times and are undetectable, but near a black hole's event horizon, something remarkable can happen. Imagine a virtual pair forming just outside the horizon. Normally, both particles would annihilate within a fraction of a second, but if one particle crosses the event horizon while the other escapes, they cannot recombine. The infalling particle carries negative energy relative to distant observers, reducing the black hole's mass. The escaping particle has positive energy and can be detected as real radiation. This process, called Hawking radiation, makes black holes glow with thermal radiation at a temperature inversely proportional to their mass. For a solar mass black hole, the Hawking temperature is about 1/10,000,000th of a degree above absolute zero, far colder than the cosmic microwave background. Such a black hole absorbs more radiation from the background than it emits through Hawking radiation, so it grows rather than shrinks. For a supermassive black hole weighing billions of solar masses, the temperature is even lower, making Hawking radiation utterly negligible. But for very small black holes, the effect becomes important. A black hole weighing about as much as a small asteroid would have a Hawking temperature above the cosmic background and would slowly evaporate. A microscopic black hole, if such things exist, would evaporate in a flash of radiation within fractions of a second. The evaporation rate accelerates as the black hole shrinks. As mass decreases, temperature increases, causing faster evaporation, which decreases mass further in a runaway process. The final moments of a black hole's life involve explosive release of energy as the last remnant of mass converts to radiation. For stellar mass black holes, the evaporation timescale is absurdly long, around 10 to the 67th power years, far exceeding the current age of the universe by incomprehensible factors. Observing Hawking radiation from astrophysical black holes is impossible with any conceivable technology. Yet, the theoretical prediction is robust, emerging from well-understood quantum field theory applied to curved spacetime. The calculation has been verified by numerous independent methods, and while we cannot observe it directly, most physicists accept Hawking radiation as real. The implications for the information paradox are severe. If a black hole forms from some specific configuration of matter, then evaporates completely via Hawking radiation, what happens to the information about the initial state? Hawking's calculation suggested the radiation is exactly thermal, meaning it contains no information about what fell in. The radiation spectrum depends only on the black hole's temperature and surface area, not on the details of the infalling matter. If the radiation truly carries no information, and the black hole eventually disappears entirely, then information has been destroyed. This violates quantum mechanics' fundamental requirement that information is conserved. Physicists have proposed numerous resolutions. Perhaps information is somehow encoded in the radiation through subtle correlations that Hawking's original calculation missed. Perhaps information escapes through non-thermal corrections to the spectrum. Perhaps the black hole never fully evaporates, leaving a stable remnant that stores all the information. Perhaps information is transferred to another universe through the singularity. Or perhaps we need a radically new understanding of quantum mechanics, or space-time, or both. The question remains unresolved despite 5 decades of intense research. Recent progress using tools from string theory, holography, and quantum entanglement has provided new insights. The ADS, CFT correspondence, a duality between gravitational theories and quantum field theories, suggests that information is indeed preserved, but in ways that require rethinking the nature of space-time. The firewall paradox, proposed in 2012, argued that preserving information might require the event horizon to become a violently energetic surface that would destroy anything trying to cross it, contradicting the classical prediction that nothing special happens at the horizon. These modern developments show that black holes continue to drive progress in fundamental physics, pushing us toward a theory that unifies quantum mechanics and gravity. While we wait for that theory, observational astronomy has made spectacular strides in detecting and studying black holes across the universe. The 2015 detection of gravitational waves from merging black holes opened an entirely new window into these objects. On the 14th of September 2015, the LIGO detectors in Louisiana and Washington simultaneously registered a distinctive pattern, a rising chirp lasting a fraction of a second, as 2 black holes weighing 36 and 29 solar masses spiraled together and merged into a 62 solar mass black hole. 3 solar masses worth of energy radiated away as gravitational waves during the collision, briefly generating power output exceeding that of all stars in the observable universe combined. The detection confirmed Einstein's century-old prediction that accelerating masses produce ripples in spacetime that propagate at light speed. Einstein himself doubted gravitational waves could ever be detected because the effects are so subtle. The LIGO detectors measure changes in arm length smaller than 1/10,000th the diameter of a proton. Achieving this sensitivity required decades of technological development, pushing laser interferometry to its absolute limits. The merging black holes compressed and stretched space itself as the waves passed Earth, alternately changing the distance between LIGO's mirrors by amounts far smaller than an atomic nucleus. The signal matched predictions from numerical relativity simulations with extraordinary precision. By analyzing the waveform, physicists extracted the masses and spins of the merging black holes, the final black hole mass, the distance to the event, and confirmation that the merger proceeded exactly as general relativity predicts. No deviations from Einstein's equations were detected, despite the extreme conditions where gravitational fields reached maximum possible intensities and space-time curvature was most severe. Since that first detection, LIGO and its European counterpart Virgo have observed dozens more black hole mergers, mapping out the population of binary black holes throughout the universe. The data reveals that stellar mass black holes are more common and more massive than pre-gravitational wave surveys suggested. Many mergers involve black holes in the 30 to 50 solar mass range, heavier than most black holes detected through X-ray observations. This discrepancy might reflect selection biases in X-ray surveys, which preferentially find black holes in close binary systems, or it might indicate multiple formation channels producing black holes with different mass distributions. The merger rate observed by LIGO implies that throughout the observable universe, black hole collisions occur roughly once per minute, each one releasing more energy in gravitational waves than all stars emit as light. We live in a universe where these violent events are routine, yet we notice them only recently because the signals are so difficult to detect. Gravitational wave astronomy is still in its infancy. Future detectors, with greater sensitivity, will observe mergers out to cosmological distances, potentially seeing black holes formed from the very first generation of stars. The space-based LISA detector, planned for launch in the 2032, will observe supermassive black hole mergers, events so powerful that their gravitational waves dominate all other signals in the millihertz frequency range. LISA will detect mergers years before they occur, watching as supermassive black holes slowly spiral inward and providing early warning for electromagnetic observatories to monitor the event across all wavelengths. The complementary approach to detecting black holes involves direct imaging. For decades, this seemed impossible. Black holes are small, even the supermassive ones, and they emit no light. Imaging an object by the absence of light against a dark background is fundamentally challenging. But black holes are surrounded by hot material in accretion disks that glow brilliantly. If you could resolve the region immediately around the event horizon, you would see a dark shadow where the black hole blocks light from the far side of the disk. This shadow would appear larger than the event horizon itself, due to gravitational lensing that bends light rays near the black hole. In April 2019, the Event Horizon Telescope collaboration announced the first direct image of a black hole's shadow, observing the supermassive black hole at the center of the galaxy M87. The image shows a bright ring of emission surrounding a dark central region. The bright ring comes from the accretion disk heated to billions of degrees. The dark shadow marks where light rays are captured by the black hole or severely redshifted. The shadow's diameter is about 42 microarc seconds, consistent with a black hole weighing 6.5 billion solar masses at M87's distance of 55 million light-years. Imaging this required linking 8 radio telescopes scattered across the globe, from Hawaii to Antarctica, creating a virtual telescope the size of Earth. The technique, called Very Long Baseline Interferometry, combines data from all telescopes to achieve angular resolution equivalent to reading a newspaper in New York from a cafe in Paris. The observations required perfect weather at all sites simultaneously, atomic clocks to timestamp data with nanosecond precision, and hundreds of petabytes of data transported on hard drives because no network could handle the transfer rate. Analysis took 2 years as teams developed novel algorithms to convert the interferometric data into an image. The result was worth the effort. The image confirmed that general relativity correctly describes space-time geometry even in the most extreme gravitational fields we can observe. The shadow size, shape, and brightness distribution matched predictions from decades of theoretical modeling. Any significant deviations would have indicated new physics beyond general relativity, but Einstein's theory passed this stringent test. In 2022, the Event Horizon Telescope released an image of Sagittarius A*, the supermassive black hole at our own galactic center. Despite being much closer than M87's black hole, Sagittarius A* is also much smaller, only 4 million solar masses compared to 6.5 billion, making the imaging challenge comparable. The material around Sagittarius A* varies on timescales of minutes due to the shorter orbital periods close to a smaller black hole, complicating the imaging process. The team had to develop new techniques to average out this variability and extract a stable image. Both images show bright rings slightly asymmetric due to relativistic beaming, where material orbiting near light speed appears brighter when moving toward us and dimmer when moving away. The asymmetry encodes information about the accretion flow structure, black hole spin, and viewing angle. Future observations with additional telescopes and at higher frequencies will sharpen the images and enable time-resolved imaging showing how material moves and changes near the event horizon. These direct images transform black holes from theoretical concepts into concrete objects we can photograph and study observationally. We are looking at the edge of the abyss, seeing light from matter in its final moments before crossing the event horizon and disappearing from the universe. What we cannot see, what remains hidden inside the horizon, drives some of the deepest questions in theoretical physics. The singularity at a black hole's center is where our understanding collapses along with space-time itself. According to general relativity, all paths inside the event horizon lead to the singularity, where density becomes infinite, curvature diverges, and the equations break down. This mathematical infinity signals that the theory is incomplete. Physical infinities typically indicate missing physics. When calculations in classical mechanics produce infinite results, it often means quantum mechanics must be applied. When quantum field theory calculations diverge, it suggests new particles or interactions at higher energies. The singularity's infinity probably indicates that quantum gravity effects, which are negligible elsewhere, become dominant and modify the space-time structure. At the Planck scale, defined by combinations of the gravitational constant, Planck's constant, and the speed of light, quantum fluctuations in space-time itself become significant. The Planck length is about 10 to the minus 35 meters, far smaller than anything we can probe experimentally. The Planck energy is about 10 to the 19 GeV, far higher than particle accelerators can reach. At these scales, space and time might become quantized, granular, foamy, or structured in ways our current theories cannot describe. Inside a black hole, as you approach the singularity, densities and curvatures increase until they reach Planck scales. At that point, classical general relativity must give way to quantum gravity. What replaces the singularity? We do not know. String theory suggests that extended objects, strings vibrating in 10-dimensional spacetime, might replace point particles and smooth out singularities. Loop quantum gravity proposes that spacetime has a discrete structure at Planck scales that prevents infinite compression. Other approaches invoke modifications to general relativity at extreme densities or exotic quantum states of matter. None of these theories are developed enough to make definitive predictions we can test observationally. The singularity remains hidden behind the event horizon, where we cannot observe it, so we cannot use observations to choose between competing theories. This observational inaccessibility frustrates physicists. Science progresses by comparing predictions to measurements, but the event horizon prevents any measurement of singularity physics. Information cannot escape from inside the horizon, so whatever happens at the singularity remains causally disconnected from the external universe. Cosmic censorship protects us from this ignorance by ensuring we never need to predict what emerges from a singularity to calculate the evolution of the outside universe. Perhaps this is nature's way of handling its own ignorance, hiding the places where the equations fail behind impenetrable barriers. Or perhaps there is a deeper principle at work, connecting the horizon's thermodynamic properties to fundamental constraints on information and entropy. Jacob Bekenstein proposed in 1972 that black holes have entropy proportional to their event horizon area. This was a radical suggestion because entropy measures disorder or information content, and black holes were thought to be perfectly ordered objects characterized only by mass, spin, and charge. But Bekenstein argued that when matter carrying entropy falls into a black hole and disappears, the total entropy of the universe would decrease unless the black hole itself gains entropy. This would violate the second law of thermodynamics, which states that total entropy never decreases. To preserve the second law, black holes must have entropy that increases when matter falls in. Bekenstein showed that defining black hole entropy as proportional to horizon area makes the second law hold, with the constant of proportionality involving Planck's constant, the speed of light, and Newton's gravitational constant. Hawking's subsequent discovery that black holes radiate with a temperature made Bekenstein's proposal concrete. A black hole's temperature is inversely proportional to its mass, and its entropy is proportional to horizon area, which scales as mass squared. Combining these gives precise formulas for black hole thermodynamics, exactly analogous to ordinary thermodynamics, but with area replacing volume as the extensive variable. The black hole entropy is enormous, about 10 to the 77 times larger than the entropy of the Sun, despite having comparable mass. This suggests that black holes are the most efficient entropy containers in the universe, packing maximum disorder into minimum volume. The microscopic origin of this entropy remained mysterious, until string theory provided a statistical mechanics derivation for certain types of black holes, showing that the entropy counts quantum states of strings and branes in configurations that look like black holes from outside. The match between Bekenstein-Hawking entropy and string theory state counting is one of string theory's most impressive successes, though it works fully only for special black holes that are not astrophysically realistic. Generalizing the calculation to Schwarzschild or Kerr black holes remains an open problem. Black hole thermodynamics implies deep connections between gravity, quantum mechanics, and information theory. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind, proposes that all information contained in a volume of space can be described by a theory living on the boundary of that region, with the amount of information limited by the boundary area rather than the volume. This is analogous to how a hologram encodes three-dimensional information on a two-dimensional surface. Black holes provide the paradigmatic example, with horizon area measuring information content. The ADS CFT correspondence, discovered by Juan Maldacena in 1997, made holography precise for certain spacetimes, showing exact equivalence between a gravitational theory in a space with negative curvature and a quantum field theory living on the boundary of that space. These developments suggest that spacetime itself might be emergent, arising from more fundamental quantum information theoretic structures rather than being a basic ingredient of reality. In this view, black holes are laboratories where the emergent nature of spacetime becomes apparent, and studying them pushes us toward a more complete understanding of quantum gravity. While theorists grapple with singularities and information paradoxes, observers continue mapping the black hole population throughout the universe. Stellar mass black holes number in the hundreds of millions in our galaxy alone, with perhaps 100 billion total in the observable universe. Most remain invisible, not accreting matter and producing no radiation. We detect them only when they are in binary systems, where their gravitational influence on a companion star becomes measurable, or when they merge and produce gravitational waves. Supermassive black holes appear to exist in virtually all large galaxies, with masses ranging from millions to tens of billions of solar masses. The correlation between black hole mass and galaxy properties suggests co-evolution, where galaxy formation and black hole growth are intimately linked through feedback processes. Active galactic nuclei, powered by accretion onto supermassive black holes, can outshine their host galaxies and inject enough energy into surrounding gas to halt star formation across the entire galaxy. This feedback might explain why the most massive galaxies are red and dead, containing old stars but forming few new ones. Intermediate mass black holes, weighing hundreds to hundreds of thousands of solar masses, remain elusive. A few candidates have been identified in globular clusters and dwarf galaxies, but their existence as a distinct population is still debated. These objects might be missing links in the black hole mass spectrum, formed through runaway collisions in dense star clusters and potentially serving as seeds for supermassive black holes. Primordial black holes, hypothesized to have formed in the very early universe from density fluctuations, could exist across a wide mass range from microscopic to thousands of solar masses. If they exist, they might constitute some or all of the dark matter, though current constraints from various observations make this unlikely for most mass ranges. Searchers continue using gravitational microlensing, looking for the brief brightening of distant stars when a primordial black hole passes between us and the star, gravitationally focusing its light. The diversity of black hole types and formation mechanisms illustrates how ubiquitous these objects are in cosmic evolution. From stellar death to galactic formation to possibly the dark matter itself, black holes participate in processes at every scale. Understanding them is essential to understanding the universe's structure and history. Looking to the far future, black holes will eventually dominate the cosmos. As the universe continues expanding and all stars burn out, star formation will cease when gas is exhausted. Galaxies will become graveyards filled with stellar remnants, white dwarfs, neutron stars, and black holes. Over incomprehensibly long timescales, dynamical interactions will eject most stars from galaxies, while some fall toward the center and are consumed by the supermassive black hole. Eventually, each galaxy will contain a single supermassive black hole surrounded by a halo of scattered stars drifting through intergalactic space. These black holes will grow slowly through occasional capture of passing stars or stellar remnants, but their primary fate is evaporation through Hawking radiation. For a solar mass black hole, this takes 10 to the 67 years. For a supermassive black hole weighing billions of suns, evaporation requires 10 to the 100 years or longer. These timescales are incomprehensible, vastly exceeding the current age of the universe. Yet quantum mechanics demands that all black holes eventually evaporate if Hawking's calculation is correct. In the final eons of the universe, after all stars have died and all matter has decayed or been consumed, only black holes will remain. They will evaporate one by one, filling the universe with thin radiation as they disappear. The largest black holes will be last to go, persisting until timescales that make the current age of the universe seem like an eye blink. When the last black hole evaporates, the universe will contain only cold, dilute radiation and perhaps some stable particles like electrons and neutrinos, spreading apart forever as expansion continues. This is the heat death scenario, the expected ultimate fate of our universe under current physics. Entropy reaches maximum, no energy remains available for work, and time loses meaning as nothing changes. Black holes represent the final stage before this ultimate equilibrium, the last complex structures to exist before everything dissolves into featureless radiation. Some cosmological models avoid heat death through different mechanisms. Cyclic models propose that the universe periodically recollapses and rebounds in a new Big Bang, though how black holes would behave across such transitions remains unclear. Models with vacuum decay suggest that the current vacuum state might be metastable, eventually tunneling to a lower energy state in a process that expands at light speed and destroys all existing structures, including black holes. Models with varying dark energy or modified gravity might permit different futures, but under the standard cosmological model with a positive cosmological constant driving accelerated expansion, heat death is inevitable and black holes are the final act. Yet, even in describing this distant future, we rely on theories that might not hold over such timescales. Quantum gravity effects, unknown physics at high energies, or phenomena we have not yet discovered could change the story entirely. The universe has surprised us before, and it will surprise us again. Black holes themselves were surprises, rejected as impossible by leading physicists before observations forced us to accept them. Dark energy, discovered in 1998, was unexpected and remains poorly understood. The universe is under no obligation to match our expectations or to be comprehensible using physics we already know. Studying black holes pushes our theories to their limits and beyond, exposing gaps in our understanding and driving the search for better theories. The singularity hidden inside challenges our deepest assumptions about space-time. Hawking radiation connects gravity to quantum mechanics and thermodynamics in unexpected ways. The information paradox questions whether information is truly conserved or whether black holes force us to revise quantum theory. The AD-S CFT correspondence suggests that space-time is emergent rather than fundamental. Every answer spawns new questions, and black holes remain at the center of these investigations. Modern black hole research encompasses an extraordinary range of topics and techniques. Numerical relativists simulate black hole mergers on supercomputers, solving Einstein's equations with finite element methods and extracting gravitational waveforms to compare with LIGO observations. String theorists construct microscopic models of black hole entropy using branes and dualities in higher dimensional spaces. Observational astronomers use radio interferometry, X-ray satellites, and optical telescopes to study accretion flows and measure black hole masses and spins. Gravitational wave astronomers analyze detector data, searching for merger signals and extracting source parameters from waveform fits. Cosmologists model black hole formation in the early universe and their role in galaxy evolution. Quantum gravity researchers explore loop quantum gravity, causal set theory, asymptotic safety, and other approaches to understanding singularities. Astrophysicists study tidal disruption events, where stars pass too close to supermassive black holes and are torn apart, creating luminous flares observable across cosmological distances. Particle physicists search for hypothetical microscopic black holes that might be produced in high-energy collisions, though none have been found. Mathematical physicists prove theorems about black hole uniqueness, stability, and thermodynamics using tools from differential geometry and analysis. Each subfield contributes pieces to the larger puzzle, slowly building toward a comprehensive understanding of these extreme objects. The pace of discovery has accelerated dramatically in recent decades. Gravitational wave detections occur regularly now, after decades of null results. The Event Horizon Telescope images provided visual confirmation of black hole existence after a century of theoretical development. X-ray and optical surveys catalogue thousands of black holes where previously we knew only a handful. Numerical simulations achieve higher accuracy and handle more complex scenarios. Theoretical frameworks like ADES, CFT, reveal deep connections between seemingly unrelated areas of physics. We stand at a privileged moment in black hole research, with new observational capabilities, revealing phenomena that were purely theoretical just years ago, and with theoretical frameworks finally mature enough to make testable predictions. Yet enormous questions remain unanswered. How do supermassive black holes form so early in cosmic history? What is the nature of the singularity, and does quantum gravity resolve it? Is information preserved or destroyed in black hole evaporation? Can cosmic censorship be proven, or are naked singularities possible? What is the black hole interior geometry really like? Do primordial black holes exist, and could they be dark matter? How do black holes influence galaxy evolution in detail? Can we use black hole observations to test general relativity in stronger field regimes? What happens to black holes in quantum gravity theories? Are there astrophysical effects we have not yet imagined? Each question represents an active research area, with competing theories and insufficient data to choose definitively between them. Answering them requires better observations, more powerful simulations, and deeper theoretical insights. The next generation of gravitational wave detectors will observe hundreds of mergers per year, mapping the black hole population across cosmic history. Next-generation Event Horizon Telescope observations will achieve higher angular resolution and time resolution, showing detailed accretion flow dynamics and testing general relativity more precisely. Space-based X-ray missions will study accretion with unprecedented sensitivity. Electromagnetic observations of gravitational wave sources will reveal black hole formation channels. Laser interferometer space antenna will detect supermassive black hole mergers and extreme mass ratio inspirals, where stellar mass objects spiral into supermassive black holes, providing precision tests of space-time geometry. Pulsar timing arrays will detect nanohertz gravitational waves from supermassive black hole binaries, opening another frequency window. Advanced simulations, incorporating magnetic fields, radiation transport, and realistic matter physics, will model accretion more accurately. Quantum gravity research might produce testable predictions for black hole physics, allowing observation to choose between theoretical frameworks. This golden age of black hole astronomy has only just begun. On the theoretical side, several promising directions offer hope for resolving long-standing puzzles. The firewall paradox and its proposed resolutions have sparked intense debate about what infalling observers experience at the horizon. Some proposals suggest the horizon becomes energetic and destroys anything crossing it, violating the equivalence principle but preserving information. Others invoke quantum error correction codes, arguing that information is redundantly encoded in the Hawking radiation through complex entanglement patterns. Still others propose that spacetime connectivity itself is more subtle than classical geometry suggests, with wormholes or non-local connections playing crucial roles. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, identifies quantum entanglement between particles with geometric connections through wormholes, providing a potential resolution to the information paradox and a concrete realization of holography. These ideas remain speculative, but they illustrate how black hole physics drives progress in fundamental theory. Loop quantum gravity offers an alternative approach to quantum gravity that makes specific predictions for black hole interiors. In this framework, space-time has a discrete structure at Planck scales, and the singularity is replaced by a region of extremely high but finite curvature. The black hole interior might connect to another region of space-time through what is called a black hole to white hole transition, with the white hole eventually ejecting the infalling matter back into the universe, but only after enormous time dilation makes the process unobservable in practice. These predictions differ from string theory and could potentially be tested through future observations of very small black holes or through signatures in Hawking radiation spectrum. Asymptotic safety, another quantum gravity approach, proposes that gravity becomes well behaved at high energies due to a non-trivial ultraviolet fixed point in the renormalization group flow. This would allow general relativity to remain valid at all energy scales without requiring a fundamentally new theory like strings or loops. Black hole singularities might be resolved by quantum corrections to Einstein's equations that become significant near the Planck scale. This program is mathematically challenging and remains less developed than string theory or loop quantum gravity, but it offers a more conservative path to quantum gravity that modifies rather than replaces general relativity. Experimental tests of these ideas remain extremely difficult because quantum gravity effects are incredibly weak at accessible energy scales. The Planck energy is about 1 billion times higher than the Large Hadron Collider can reach. Observing quantum gravity effects requires either going to impossibly high energies or finding extremely sensitive low-energy probes where tiny quantum gravity corrections might be detectable. Black holes, neutron stars, and cosmological observations offer the best hope for such tests. Variations in light speed for different energies, violations of Lorentz invariance, modifications to black hole entropy formulas, or signatures in the cosmic microwave background could all potentially reveal quantum gravity effects if we can measure precisely enough. No smoking gun has been found yet, but searches continue and instrumental capabilities improve steadily. The interplay between observation and theory drives progress on both fronts. Observations provide the data that theories must explain and occasionally reveal phenomena that no theory predicted, forcing new theoretical developments. Theories make predictions that guide observers toward interesting targets and suggest what signatures to look for. Black holes exemplify this synergy. Einstein's theory predicted their existence. Astrophysical observations confirmed they exist and measured their properties. Those measurements revealed puzzles like early supermassive black holes that challenge formation theories. New theories like dark stars emerge to explain the observations. Those theories make additional predictions that guide future observations. The cycle continues with each iteration refining our understanding. What began as a peculiar mathematical curiosity in Schwarzschild's solution has become a central element of modern astrophysics and theoretical physics. Black holes are no longer exotic speculations, but observed components of the universe as real as stars and galaxies. We have photographed their shadows, we have detected their collisions, we have measured their masses and spins, we use them to test fundamental physics in extreme conditions, impossible to replicate in laboratories. They have transformed from theoretical abstractions into observational facts, yet they retain their mystery and continue to challenge our deepest understanding of nature. The journey from Mitchell's dark stars to the Event Horizon Telescope images spans more than 2 centuries and encompasses some of the greatest intellectual achievements in human history. General relativity ranks among the most beautiful theories ever constructed, with experimental confirmation across 60 orders of magnitude in energy scale. Quantum mechanics reveals the probabilistic quantum nature of reality and powers modern technology. Combining them to understand black holes pushes physics to its limits and beyond, requiring new mathematics, new concepts, and new ways of thinking about space, time, and information. Every major advance in physics has expanded our view of the universe and our place within it. Copernicus displaced Earth from the center of the solar system. Galileo showed that the heavens obey the same laws as Earth. Newton unified celestial and terrestrial mechanics. Darwin demonstrated our connection to all life. Einstein revealed spacetime's malleability. Quantum mechanics exposed reality's fundamental uncertainty. Black hole physics continues this tradition, revealing that spacetime itself might be emergent, that information and entropy connect to geometry, that singularities hide behind horizons, and that the vacuum itself bubbles with quantum activity. Each insight changes how we understand reality at the deepest level. Looking ahead, several major observational milestones will mark the next phase of black hole astronomy. The first image of Sagittarius A times has been released, but higher resolution images will reveal more details of the accretion flow structure and enable time-resolved observations showing how material orbits and accretes. The first detection of a supermassive black hole merger through electromagnetic observations, combined with gravitational waves, will reveal the full dynamics of these titanic collisions. The first measurement of black holes spin through X-ray spectroscopy, precise enough to test general relativity predictions, will provide a stringent test of the Kerr solution. The first detection of Hawking radiation, or quantum effects, near a black hole horizon would revolutionize physics, though this remains extremely challenging and might require decades or centuries to achieve. The first direct test of cosmic censorship by observing whether naked singularities can exist would resolve one of general relativity's oldest questions. The first detection of intermediate mass black holes in globular clusters would fill the gap in the black hole mass spectrum and clarify formation channels. Each of these milestones will advance our knowledge and likely raise new questions we have not yet imagined. Scientific progress rarely provides final answers. Instead, it reveals new layers of complexity and new questions to investigate. Black hole research exemplifies this pattern. 70 years ago, we debated whether they could exist. Now we photograph them, detect their mergers, and use them to probe quantum gravity. What will we know 70 years from now? The answer depends on continued investment in observational facilities, theoretical research, and the training of new scientists. Astronomy requires long-term commitment because designing, building, and operating major observatories spans decades. The Event Horizon Telescope, built on decades of radio interferometry development, LIGO required 40 years from initial concept to first detection. Future facilities like the Laser Interferometer Space Antenna, the next-generation Event Horizon Telescope, and 30-meter class ground-based telescopes will take decades to complete. Theoretical progress requires supporting researchers working on problems where applications might not emerge for generations. The scientists who will make the next breakthroughs are students today or not yet born. Ensuring they have opportunities to pursue these questions is essential if we want to continue expanding human knowledge. Black holes also capture public imagination in ways that benefit science communication and education. They appear in science fiction, popular science books, documentaries, and public lectures. Their extreme nature makes them compelling subjects even for those without technical background. The dramatic imagery of matter spiraling into a bottomless pit, space-time warping so severely that nothing escapes, and stars torn apart by tidal forces resonates emotionally while illustrating real physics. This public fascination translates into support for scientific research funding and inspires young people to pursue careers in science. Many physicists and astronomers trace their interest to childhood encounters with black holes through books or planetarium shows. Maintaining and expanding this public engagement is crucial for the long-term health of the scientific enterprise. Museums, planetariums, science centers, and media have important roles in translating complex research into accessible content. Scientists themselves must communicate their work beyond specialized journals, writing popular accounts, giving public talks, and engaging with journalists. The balance between technical accuracy and accessibility is challenging but essential. Oversimplification misleads while excessive jargon excludes. Finding the right level requires understanding the audience and iterating based on feedback. The best science communication conveys not just facts but the process of science, how we know what we know, why we trust certain conclusions, what remains uncertain, and how research actually works, with all its false starts, blind alleys, and gradual progress. Black holes provide excellent case studies because the history includes dramatic shifts in understanding, heated debates that were eventually resolved by observations, predictions made decades before confirmation, and ongoing mysteries where honest uncertainty remains. As we have seen, black holes connect to virtually every area of modern physics and astronomy. General relativity describes their classical geometry. Quantum mechanics governs Hawking radiation and the information paradox. Thermodynamics applies through black hole entropy and temperature. Particle physics appears in models of singularity, resolution, and quantum gravity. Astrophysics explains their formation through stellar collapse. Cosmology traces their role in galaxy evolution and possibly dark matter. Observational astronomy detects them through electromagnetic radiation, gravitational waves, and direct imaging. Mathematical physics provides the tools to solve Einstein's equations and prove theorems about black hole properties. Each field contributes essential insights, and progress requires integrating knowledge across traditional boundaries. This interdisciplinary nature makes black holes both challenging and exciting to study. Researchers must understand multiple areas and collaborate across specializations. A gravitational wave astronomer needs to understand general relativity, signal processing, statistical analysis, and astrophysics. A black hole theorist needs mathematical physics, quantum field theory, and familiarity with observational constraints. The era of individual scientists mastering entire fields has passed. Modern research requires teamwork and communication across disciplines. The Event Horizon Telescope collaboration includes hundreds of scientists from dozens of institutions. LIGO involves thousands of researchers and engineers. Large simulations run on supercomputers, maintained by specialist teams. Progress depends on diverse expertise, working together toward common goals. This collaborative nature reflects broader trends in science, where problems become more complex and specialized knowledge deepens. Building the infrastructures needed for cutting-edge research requires resources beyond what single institutions can provide, leading to international collaborations and shared facilities. The Large Hadron Collider at CERN, the Hubble Space Telescope, the Atacama Large Millimeter Array, and the James Webb Space Telescope exemplify this trend. Black hole research benefits enormously from these investments and contributes to justifying them by delivering spectacular results that validate the expense and effort. In conclusion, black holes represent some of the universe's most extreme and fascinating phenomena. From stellar remnants weighing a few solar masses to supermassive monsters billions of times heavier, they shape cosmic evolution and challenge our deepest understanding of physics. General relativity predicted them, observations confirmed them, and ongoing research continues revealing new aspects of their nature and role in the cosmos. They mark the ultimate victory of gravity over all other forces, compressing matter to infinite density according to classical theory, while quantum mechanics suggests more complex resolutions we have not yet fully understood. They evaporate through Hawking radiation, connecting gravity, quantum mechanics, and thermodynamics in unprecedented ways. They violate intuitions about space and time, with event horizons that mark one-way boundaries and interiors where the future inevitably leads to the singularity. They serve as natural laboratories for extreme physics, with gravitational fields and space-time curvatures far beyond anything achievable in terrestrial experiments. They populate the universe at all scales, from stellar masses to galactic centers to possibly microscopic primordial remnants. They determine galaxy evolution through feedback from active galactic nuclei. They merge in spectacular collisions, generating gravitational waves detectable across the universe. They might constitute part or all of dark matter. They will dominate the far future as stars die and matter decays, persisting until they too evaporate in the final eons before heat death. Studying them requires our most sophisticated theories and observational techniques, while still leaving fundamental questions unanswered. They inspire public fascination and drive recruitment into physics and astronomy. They exemplify humanity's quest to understand nature at its deepest levels, regardless of immediate practical applications. The universe contains these objects, whether or not we study them, but studying them reveals truths about reality that we could learn no other way. From Michel's theoretical speculation to Einstein's reluctant prediction to Chandrasekhar's calculations, to Oppenheimer's collapse models, to Wheeler's popularization, to Hawking's radiation, to LIGO's detections, to the Event Horizon Telescope's images, black hole physics has progressed through contributions from many brilliant minds over more than 2 centuries. The journey continues with new observations, new theories, and new scientists asking questions we have not yet imagined. The abyss looks back at us, challenging us to understand what lies within. Space and time curve dramatically. Matter compresses beyond imagination. Information might be lost or preserved through subtle quantum correlations. Singularities hide behind horizons. The vacuum fluctuates with quantum energy. Gravitational waves ripple through the cosmos. Event horizons mark points of no return. Black holes exist, and they are spectacular. The universe is stranger and more wonderful than we knew, and black holes prove it. They wait in the darkness, bending space-time, capturing light, and defying our attempts at complete understanding. But with each observation and each theoretical advance, we come closer to comprehending these ultimate objects. The journey into the abyss continues, and there is no end in sight. But to truly understand black holes, we must explore the physics of matter falling toward these cosmic drains, the extraordinary processes that make them visible despite their darkness, and the specific objects that have taught us the most about how nature behaves at its most extreme. When gas falls toward a black hole, it does not plunge directly inward. Conservation of angular momentum forces the material into orbit, forming a disk structure where the inner edge spirals closer to the event horizon, while the outer regions extend outward for thousands or millions of kilometers. This accretion disk is where the real action happens, where gravitational potential energy converts to heat and radiation with efficiency that dwarfs all other energy sources in the universe. The physics of accretion disks involves hydrodynamics, magnetohydrodynamics, radiation transport, and general relativistic effects all operating simultaneously in extreme conditions. Gas orbiting close to a black hole moves at substantial fractions of light speed. At the innermost stable circular orbit, orbital velocities reach about half the speed of light for non-rotating black holes, and even higher for rapidly spinning ones. These velocities create tremendous shear between adjacent layers of the disk orbiting at slightly different rates. The faster inner regions drag against the slower outer regions, creating friction that heats the gas. This is not friction in the everyday sense of rough surfaces rubbing together. In accretion disks, friction arises from turbulence generated by magnetohydrodynamic instabilities. The magnetorotational instability, discovered in astrophysical contexts by Stephen Balbus and John Hawley in 1991, shows that even weak magnetic fields threading a differentially rotating disk become unstable and amplify exponentially. The growing magnetic fields create turbulent eddies that transport angular momentum outward and allow matter to spiral inward. Without this mechanism, accretion disks could not function efficiently because gas would remain in stable orbits rather than falling into the black hole. The magnetorotational instability solved a decades-old problem in disk physics and revolutionized our understanding of accretion. As turbulence transfers angular momentum outward, the gas slowly spirals inward while heating up. The temperature increases dramatically in the inner regions, reaching millions of degrees within a few Schwarzschild radii of the event horizon. At these temperatures, the gas emits primarily in X-rays and ultraviolet light. The radiation pressure from this emission becomes so intense that it can influence the disk structure, creating a complex interplay between gravity trying to pull matter inward, centrifugal force from rotation trying to fling it outward, and radiation pressure trying to blow it away. The balance between these forces determines the accretion rate, disk structure, and luminosity. For accretion rates below a critical threshold, the disk remains geometrically thin and optically thick, meaning it is flattened like a pancake and opaque to its own radiation. These standard thin disks, first modeled by Nikolai Shakura and Rashid Sunyaev in 1973, radiate efficiently and reach the luminosities observed in many quasars and X-ray binaries. For higher accretion rates approaching or exceeding the Eddington limit, radiation pressure puffs up the disk, creating a geometrically thick structure where photons get trapped and advected inward with the flow rather than escaping. These advection-dominated accretion flows are less efficient at converting gravitational energy to radiation, but they can sustain higher accretion rates. For very low accretion rates, the disk becomes geometrically thick and optically thin, forming a hot, radiatively inefficient accretion flow where most energy remains locked in the gas rather than radiating away. Sagittarius A times appears to accrete in this mode, explaining why it is so dim despite being a 4 million solar mass black hole. The observed luminosity is millions of times lower than it would be if accreting at the Eddington rate, implying that our galactic center black hole is severely underfed. The different accretion modes produce different observational signatures. Thin disks generate thermal spectra peaked in ultraviolet or X-rays depending on black hole mass. Advection-dominated flows produce harder X-ray spectra and sometimes gamma rays. Radiatively inefficient flows are dim and difficult to detect. By observing the spectrum and luminosity, astronomers can infer which mode dominates and constrain the accretion rate. Time variability provides additional information since different accretion modes exhibit different types of flickering and periodic variations. The inner edge of the accretion disk marks the innermost stable circular orbit, which depends on black hole spin. For a non-rotating Schwarzschild black hole, this orbit lies at 3 times the Schwarzschild radius, or 6 times the black hole mass in geometric units. Inside this radius, no stable orbits exist, and gas inevitably plunges into the event horizon on a timescale of milliseconds to seconds for stellar mass black holes, or hours to days for supermassive ones. For rotating Kerr black holes, the innermost stable orbit moves closer to the horizon, reaching as close as the event horizon itself for maximally rotating black holes with spin aligned to the orbital motion. This difference has profound observational consequences. By measuring X-ray spectra and looking for features from the inner disk edge, astronomers can locate the innermost stable orbit and thereby determine black hole spin. Ion emission lines are particularly useful for this because iron is abundant in accretion disks and produces a strong emission line at 6.4 keV. This line is broadened and skewed by relativistic effects including Doppler shifts from orbital motion, gravitational redshift, and light bending near the black hole. The detailed line shape encodes information about the disk geometry and black hole spin. Fitting models to observed ion line profiles has become a primary method for measuring black hole spin in both stellar mass and supermassive systems. Results indicate that many black holes rotate rapidly, with spins reaching 50 to 98% of the maximum possible value. These high spins tell us about black hole formation and growth history. A black hole formed from stellar collapse inherits the progenitor star's angular momentum, typically producing moderate spin rates. If the black hole then accretes from a coherent disk where material always falls in from the same direction, the cumulative angular momentum addition spins up the black hole toward maximum rotation. If instead the black hole grows through mergers or chaotic accretion from random directions, the angular momentum adds less coherently, and the final spin remains moderate. The observed distribution of spins constrains which growth mechanisms dominated for different black hole populations. Supermassive black holes generally show high spins, suggesting they grew primarily through orderly accretion rather than random mergers, though some lower spin systems exist and probably grew through more chaotic processes. Not all matter in the accretion disk falls into the black hole. Some is ejected in powerful outflows and jets that can extend for millions of light-years into intergalactic space. These jets rank among the most spectacular phenomena in the universe, channeling enormous power into collimated beams that propagate at near light speed and remain coherent over vast distances. The mechanism generating jets remains incompletely understood despite decades of research, but the essential ingredients are known. A spinning black hole, a magnetic field threading the accretion disk or anchored to the event horizon, and differential rotation create conditions for extracting rotational energy from the black hole itself or from the inner accretion flow. The Blandford-Znajek mechanism, proposed in 1977, shows how magnetic fields in the ergosphere of a rotating black hole can tap the hole's rotational energy and convert it to electromagnetic energy that drives relativistic outflows along the rotation axis. Simulations show that magnetic fields get wound up by differential rotation, creating a helical field structure that collimates plasma into narrow jets and accelerates it through magnetic pressure gradients and electromagnetic forces. The details depend sensitively on field geometry, accretion rate, and black hole spin, creating a zoo of different jet types observed in active galactic nuclei and microquasars, the stellar mass black hole systems that produce jets analogous to those from supermassive black holes, but on smaller scales. Blazars are active galactic nuclei where jets point nearly directly at Earth, creating extreme Doppler boosting that amplifies the observed luminosity and compresses the emission timescale. These objects can vary on timescales of hours and reach luminosities exceeding 1,000 trillion suns. The gamma-ray emission from blazars makes them among the brightest sources in the gamma-ray sky, detectable by satellites like Fermi and ground-based Cherenkov telescopes that observe the particle cascades created when high-energy gamma rays interact with Earth's atmosphere. Studying blazars provides information about jet physics, magnetic field structure, and particle acceleration mechanisms that produce the observed non-thermal radiation extending from radio waves to TV gamma rays. Radio galaxies show jets viewed more from the side, revealing their extended structure. The jets terminate in giant radio lobes, where the outflow plows into intergalactic gas, creating shocks and accelerating particles to ultra-relativistic energies. These lobes can extend for millions of light-years, dwarfing their host galaxies and pumping enormous energy into the surrounding environment. The radio emission traces synchrotron radiation from electrons spiraling in magnetic fields, and the observed brightness distribution maps the magnetic field structure and electron energy distribution. Some radio jets show knots and hotspots indicating internal shocks, where faster-moving material catches up to slower ejecta, creating localized regions of enhanced emission. Very long baseline interferometry reveals jet structure on scales down to a few Schwarzschild radii, showing that jets emerge from regions very close to the event horizon and are already collimated and accelerating at those small scales. The interaction between jets and the surrounding gas provides a feedback mechanism that affects galaxy evolution. The mechanical energy deposited by jets heats intergalactic gas, preventing it from cooling and falling into the galaxy to form new stars. This AGN feedback, as it is called, might explain why the most massive galaxies are quiescent with little ongoing star formation. Without AGN feedback, simulations produce galaxies far more massive than any observed, because gas would cool efficiently and form stars at very high rates. Including feedback from black hole accretion and jets in simulations produces galaxy masses and properties matching observations, suggesting that supermassive black holes regulate their host galaxy growth and create the observed correlation between black hole mass and galaxy bulge properties. The feedback operates as a self-regulating cycle where vigorous star formation provides gas that feeds the black hole, increasing accretion, luminosity, and jet power until the outflows become strong enough to expel remaining gas and quench both star formation and black hole growth. The system then quiets until new gas arrives through mergers or intergalactic infall, restarting the cycle. Observations show that this episodic activity pattern is common, with many galaxies showing evidence for past cycles of activity now shut off. Tidal disruption events provide a different window into black hole accretion physics. When a Cree star passes too close to a supermassive black hole, tidal forces from the differential gravity between the near and far sides of the star exceed the star's self-gravity. The star gets stretched into a long stream with half the material remaining bound to the black hole, while the other half gets ejected at high velocity. The bound material has a range of binding energies and angular momenta, causing it to circularize at different radii. The gas collides with itself, dissipates orbital energy through shocks, and settles into an accretion disk that feeds the black hole over months to years. The resulting flare can reach luminosities exceeding 1 billion suns and be observed across cosmological distances. Tidal disruption events occur relatively rarely, perhaps once per 10,000 years per galaxy, but surveys monitoring millions of galaxies find several events per year. These transients provide laboratories for studying accretion physics because we observe the process from beginning to end rather than seeing only the steady state that characterizes most active galactic nuclei. The light curve, spectrum, and evolution encode information about black hole mass, spin, tidal disruption physics, and disk formation timescales. Different types of stars produce different signatures when disrupted. Main sequence stars like our Sun produce hydrogen-rich spectra, while white dwarfs produce helium or carbon-oxygen-rich material, depending on their composition. The disruption radius depends on stellar density, lying outside the event horizon for main sequence stars and giant stars, but inside the horizon for neutron stars and white dwarfs around the most massive black holes. Intermediate mass black holes in globular clusters might be detectable through tidal disruption events, since they are too small to accrete significant gas under normal circumstances, but would flare dramatically when occasionally disrupting a star. Searches for such events continue, but have not yet produced confirmed detections. Gravitational waves from extreme mass ratio inspirals, where stellar mass objects spiral into supermassive black holes, will provide another probe of strong field gravity. Unlike the comparable mass binary mergers that LIGO detects, extreme mass ratio inspirals involve mass ratios of 1,000,000 to 1 or greater. The small object, a stellar mass black hole, neutron star, or white dwarf, orbits many thousands of times, while gradually spiraling inward, emitting gravitational waves that encode a map of the space-time geometry around the supermassive black hole. These systems will be prime targets for LISA, the Laser Interferometer Space Antenna planned for launch in the 2030s. LISA will observe gravitational waves in the millihertz frequency range, where terrestrial detectors cannot operate due to seismic noise and gravity gradient noise from local mass fluctuations. In space, LISA's 3 spacecraft, separated by 2.5 million kilometers, form a triangular detector that can observe supermassive black hole mergers out to cosmological distances and track extreme mass ratio inspirals for years before the UNES final plunge. The gravitational waveforms from these inspirals will test general relativity with unprecedented precision, measuring deviations from the Kerr geometry at the part per thousand level or better, and potentially detecting signatures of exotic alternatives like boson stars, gravastars, or other objects that might masquerade as black holes. If deviations are found, they would indicate new physics beyond general relativity or confirm that the no-hair theorem fails and black holes have additional structure not captured by the Kerr solution. Even null results strengthen our confidence that Einstein's theory correctly describes gravity even in the most extreme environments. The prospect of detecting such deviations drives theoretical work on alternative theories and exotic compact objects. Some proposals suggest that quantum corrections to general relativity might become significant at or near the event horizon, creating measurable signatures in gravitational waves or electromagnetic emissions. Others propose that dark matter or dark energy might accumulate near black holes and alter their properties. Still others investigate whether astrophysical black holes might possess scalar hair or other fields that violate the classical no-hair theorem. Testing these ideas requires precision measurements, comparing observations to predictions, and gravitational wave astronomy provides the precision needed for meaningful tests. Pulsar timing arrays offer a complementary approach to gravitational wave detection in a different frequency range. Pulsars are rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses. Some pulsars are extraordinarily stable clocks with periods constant to better than 1 part in a billion, making them sensitive probes of space-time perturbations. Gravitational waves passing between Earth and a pulsar alternately compress and stretch space-time, slightly changing the light travel time and creating detectable variations in pulse arrival times. An array of dozens of pulsars distributed across the sky forms a galaxy-scale gravitational wave detector sensitive to nanohertz frequencies, corresponding to periods of months to years. At these frequencies, the dominant sources are supermassive black hole binaries formed when galaxies merge. 2 supermassive black holes orbiting each other with periods of months or years emit gravitational waves that create a stochastic background, a hum of overlapping signals from binaries throughout the universe. Several pulsar timing array projects have reported evidence for this background at the expected amplitude, though confirmation requires additional data and analysis. Individual loud binary systems might also be detectable above the background, and tracking their evolution could provide early warning years before the final merger, when the system will become detectable by LISA. The multi-messenger observations combining electromagnetic and gravitational wave data will reveal the full picture of how supermassive black holes merge and how the surrounding gas responds. Some of the most famous individual black holes have taught us crucial lessons about their species. Cygnus X1, the first stellar mass black hole identified, continues to be studied intensively. Recent observations refined its mass to 21 solar masses, substantially heavier than earlier estimates, and determined that it rotates very rapidly with spin parameter above 0.95. The system consists of the black hole and a blue supergiant star in a tight 5.6-day orbit, with the black hole accreting material via stellar wind from the companion. The variability of the X-ray emission spans timescales from milliseconds to months, reflecting different physical processes from oscillations in the inner accretion disk to long-term changes in the wind-driven accretion rate. GRS 1915+105 holds the record for the most massive stellar mass black hole in our galaxy at roughly 12 to 14 solar masses, and exhibits extraordinary variability patterns that have puzzled observers for decades. The system shows multiple distinct states with different X-ray colors and timing properties, and it transitions between states in complex sequences. Some states involve regular oscillations with periods near 1 minute, while others show chaotic flickering on all timescales. The source also produces relativistic jets that have been tracked moving outward at apparent superluminal velocities due to projection effects when the jet points nearly toward Earth. These observations probe the connection between accretion states and jet production, showing that jets turn on and off as the inner accretion flow changes configuration. V. 404. Cygni became famous during its 2015 outburst when it brightened dramatically and produced some of the most extreme variability ever observed from a black hole. Binary. The X-ray flux varied by factors of hundreds on timescales of hours, and the optical brightness fluctuated wildly on timescales of minutes or seconds. The behavior suggested a precessing and wobbling inner accretion flow, where the axis of the flow changed direction on short timescales, possibly driven by the Lense-Thirring effect, where the black hole's spin drags spacetime and causes orbits to precess. The optical and X-ray variability were correlated in complex ways that are still being analyzed. Such extreme systems push our theoretical understanding and challenge models to explain behavior more chaotic than anything in standard scenarios. In the realm of supermassive black holes, M87 star, the black hole imaged by the Event Horizon Telescope weighs 6.5 billion solar masses and powers a jet extending 5,000 light-years from the galaxy. The jet has been observed for over a century and shows structures that appear to move at several times light speed due to relativistic beaming. The 2019 Event Horizon Telescope image revealed an asymmetric ring with a brighter southern side consistent with Doppler boosting from orbital motion. The black hole's spin was estimated from the jet structure and polarization measurements to be substantial, though probably not maximal. Follow-up observations in 2021 showed that the bright region had rotated around the ring, demonstrating that the accretion flow structure changes on timescales of months to years. This variability will be crucial for refining models of the emission region and testing whether simulations can reproduce the observed evolution. 3C279 is a blazar whose jet points almost directly at Earth, making it one of the brightest gamma-ray sources in the sky. The Event Horizon Telescope observed this object and resolved structure on scales of 10 to 20 Schwarzschild radii, showing the base of the jet emerging from the vicinity of the supermassive black hole. The orientation creates extreme Doppler boosting with beaming factors reaching 20 or more, meaning the observed luminosity is boosted by these factors compared to what an observer viewing from the side would see. The gamma-ray emission varies dramatically on timescales as short as minutes, implying emission regions smaller than light minutes across despite being 5 billion light-years away. Explaining this combination of rapid variability and extreme luminosity requires invoking relativistic beaming, magnetic reconnection, and possibly shock acceleration in the jet, with debates continuing about the relative importance of different mechanisms. NGC 1277 is a lenticular galaxy that contains a black hole weighing 17 billion solar masses, one of the most massive known, and this mass constitutes an astonishing 14% of the galaxy's total stellar mass. Typical supermassive black holes represent only about 0.1% to 1% of their host bulge mass, making NGC 1277 a major outlier. The galaxy appears to have experienced very little evolution since formation, with stars all about the same age suggesting a single intense burst of star formation followed by quiescence. The oversized black hole might have formed through different processes than typical supermassive black holes, possibly involving direct collapse of a massive gas cloud in the early universe or an unusually efficient feeding period. Studying extreme outliers helps define the range of possible formation scenarios and tests whether the black hole galaxy correlations are truly fundamental or just statistical averages. TON 618 is one of the most luminous quasars known and hosts a black hole estimated at 66 billion solar masses, based on the width of its emission lines and luminosity. At this mass, the Schwarzschild radius exceeds 1,300 astronomical units, larger than the Kuiper belt in our solar system. The quasar's luminosity reaches 4x10, 40 watts, equal to about 140 trillion suns, meaning it outshines entire galaxy clusters. Such extreme objects test the upper limits of black hole growth and require sustained feeding at or above the Eddington limit for hundreds of millions of years. Their existence implies that either early universe conditions permitted unusually efficient black hole growth, or that heavy seed black holes formed through direct collapse or dark star scenarios as discussed earlier. The Phoenix cluster contains a supermassive black hole that is accreting at remarkable rates and producing powerful feedback that affects the entire cluster. The black hole is converting several hundred solar masses per year into radiation and mechanical energy through its jets, depositing this energy into the surrounding intracluster medium and heating it enough to balance radiative cooling. Without this energy input, the hot gas would cool and condense onto the central galaxy at rates of thousands of solar masses per year, triggering an intense starburst. The balance is precarious, with observations showing that star formation does occur at rates of hundreds of solar masses per year, significantly higher than typical brightest cluster galaxies, but well below what would result without feedback. The Phoenix cluster illustrates the ongoing battle between cooling and heating that regulates galaxy growth in dense environments. OJ 287 is a binary supermassive black hole system where two black holes orbit each other with a period of approximately 12 years. The system shows periodic optical outbursts every 12 years with a double-peaked structure where two outbursts occur separated by about 1 year. The pattern has been observed for over a century and matches models where the smaller black hole, weighing roughly 150 million solar masses, plunges through the accretion disk of the larger black hole, weighing about 18 billion solar masses, twice per orbit, creating the two outbursts. The orbital period is decreasing due to gravitational wave emission, and precise timing of the outbursts tests general relativity predictions for orbital decay and provides estimates of system parameters. This binary is close enough to merger that it should coalesce within about 10,000 years, well before LISA can observe it, but it provides a nearby laboratory for binary supermassive black hole physics during the late inspiral phase before mergers. The question of how binary supermassive black holes actually merge presents significant theoretical challenges known as the final parsec problem. When two galaxies merge, their central black holes initially remain separated by kiloparsecs as they sink toward the merged galaxy's center through dynamical friction, where gravitational interactions with stars transfer momentum and cause the black holes to lose orbital energy. As the separation shrinks below about 1 parsec, the density of stars available to carry away orbital energy decreases because the binary has already scattered away most stars on intersecting orbits. Further orbital decay slows dramatically, and in simple models, the binary stalls at separations of a parsec or less, never reaching the small separations where gravitational wave emission becomes efficient enough to drive the merger to completion. This final parsec problem seemed to imply that many binary supermassive black holes should remain stalled in galactic centers rather than merging, yet observations show that major galaxy mergers are common throughout cosmic history, and we do not see numerous stalled binaries. Something must be resolving the problem. Several mechanisms have been proposed. In non-spherical galaxy potentials, such as triaxial ellipsoids, chaotic orbits can continually feed new stars into the binary's loss cone, providing fresh material to carry away orbital energy and allowing continued hardening. Gas accretion onto the binary can also extract angular momentum through hydrodynamic torques and drag forces. Massive perturbers, like infalling satellite galaxies or globular clusters, could scatter the binary into tighter orbits. Any combination of these effects might operate in real systems. Recent simulations incorporating realistic galaxy models suggest that the final parsec problem might not be as severe as simple models indicated, with merger times perhaps extending to tens or hundreds of millions of years rather than stalling entirely. Gravitational wave observations will eventually test these models by measuring the merger rate of supermassive black hole binaries and determining whether it matches the galaxy merger rate or shows a deficit indicating stalling. Alternative scenarios to black holes have been proposed over the decades, though none have gained broad acceptance because they struggle to match observations while black holes explain data elegantly. Gravastars, proposed as alternatives, replace the event horizon and singularity with a thin shell of ultra-stiff matter surrounding a region of vacuum energy. The vacuum creates gravitational repulsion that prevents collapse to a singularity, while the shell prevents external observers from distinguishing the object from a black hole except through subtle differences in the space-time geometry, very close to the surface. Hypothetically, gravastars could have formed in the early universe under special conditions and would be stable configurations that mimic black holes. However, no compelling formation mechanism has been identified, and the quantum equations of state required for the shell seem unphysical. Observations sensitive to the near-horizon region, such as gravitational wave signals from mergers or event horizon telescope imaging, should be able to distinguish gravastars from black holes if they exist, and so far all data favors black holes. Boson stars, hypothetical objects made of bosonic particles held together by self-gravity and quantum pressure, could also potentially mimic black holes. These objects would have no event horizon but could be very compact and dark, making them difficult to distinguish from black holes in some observations. Unlike gravastars, boson stars have well-defined equations of state based on scalar field theory, and certain theories of physics beyond the standard model predict particles that could form such objects. The challenge is that boson stars are generally less stable than black holes and would likely be disrupted in binary mergers or violent astrophysical processes that black holes survive easily. Gravitational wave observations of mergers show ring-down signals consistent with black hole quasi-normal modes and inconsistent with boson star oscillations, providing strong evidence against the boson star interpretation for LIGO's observed mergers. Wormholes, hypothetical tunnels through space-time connecting distant regions, could theoretically exist as solutions to Einstein's equations, but they require exotic matter with negative energy density to hold them open. Quantum field theory allows negative energy densities in certain circumstances through the Casimir effect or squeezed vacuum states, but the amounts available are far too small to stabilize astrophysical scale wormholes. Traversable wormholes, if they exist, would create time travel paradoxes, since anything traveling through the wormhole faster than light could in principle reach its own past. Most physicists believe that nature prohibits such paradoxes through unknown mechanisms that prevent wormhole formation or traversal. Some theories propose that black hole interiors might connect to other universes through wormhole-like structures, but these connections are not traversable and do not create paradoxes. The ER equals EPR proposal mentioned earlier suggests that quantum entanglement between particles creates microscopic wormholes connecting them, though these are far too small for anything macroscopic to pass through. Naked singularities. Singularities without event horizons would violate cosmic censorship and create profound problems for physics by allowing unpredictable influences to emerge from the singularity and affect the external universe. Most physicists believe naked singularities cannot form from realistic initial conditions, though rigorous proof remains elusive. Some studies have found that small perturbations to configurations that appear to produce naked singularities actually generate event horizons before the singularity forms, suggesting that nature is robust against naked singularity formation. Other investigations explore borderline cases and try to determine the most general statement of cosmic censorship that might be provable. The question connects to fundamental issues about determinism and predictability in physics, since naked singularities would undermine the ability to predict future evolution from present conditions. Primordial black holes, if they exist, represent a class of objects formed by density fluctuations in the very early universe, rather than by stellar collapse. During the radiation-dominated era before recombination, regions where density exceeded a critical threshold could collapse directly to form black holes, with masses set by the cosmic horizon scale at the time of formation. Depending on when they formed, primordial black holes could range from microscopic masses below 1 gram to thousands of solar masses. Those below about 10-15 grams would have evaporated through Hawking radiation by now, leaving observable signatures in the form of antimatter or other exotic particles. Those above this mass persist to the present day and could constitute some fraction of dark matter. Observational constraints from gravitational microlensing, cosmic microwave background effects, Big Bang nucleosynthesis, and dynamical effects in stellar systems exclude primordial black holes from being all of the dark matter for most mass ranges, but certain windows remain open. The window from roughly 20 to 100 solar masses is particularly interesting because it overlaps with the masses of black holes detected by LIGO. Some researchers propose that LIGO might be detecting primordial black hole mergers rather than black holes formed from stellar collapse, though most evidence now favors the stellar origin for the majority of LIGO's detections. Binary formation mechanisms work more naturally for stellar black holes than primordial ones, and the observed mass distribution and spin parameters match stellar evolution predictions reasonably well. Nonetheless, a small fraction of LIGO's detections might involve primordial black holes, and future observations may be able to distinguish the populations through statistical properties of the mass function and merger rate evolution with redshift. Black holes in string theory take on additional richness because string theory operates in 10-dimensional spacetime with 6 extra dimensions compactified to tiny scales. Black holes in higher dimensions behave differently from 4-dimensional ones, with different horizon topologies and thermodynamic properties. Some higher dimensional black holes have pancake-shaped or ring-shaped horizons rather than spherical surfaces. Black ring solutions exist where the horizon has the topology of a torus rather than a sphere. These exotic solutions might seem irrelevant to astrophysics since the extra dimensions are microscopic, but they provide theoretical laboratories for exploring black hole physics and testing ideas about quantum gravity. String theory also allows construction of black hole microstates, specific string and brane configurations that have the same macroscopic properties as a black hole but differ microscopically. Counting these microstates reproduces the Bekenstein-Hawking entropy formula for certain supersymmetric black holes, providing microscopic justification for black hole thermodynamics. The fuzzball proposal suggests that all black hole microstates are actually fuzzy quantum superpositions of strings and branes extending throughout the black hole interior rather than concentrated at a singularity. If correct, this would mean there is no true singularity or sharp event horizon at the microscopic level, only effective descriptions that emerge when averaging over many quantum microstates. The proposal offers a potential resolution to the information paradox by avoiding information loss entirely, since information is stored in the fuzzy structure rather than being destroyed at a singularity. However, the fuzzball program faces significant technical challenges and has not yet produced testable predictions that distinguish it from alternative approaches to quantum black holes. Looking toward future observations, the Next Generation Event Horizon Telescope will expand to include more telescopes, including stations in space, enabling higher angular resolution and filling in coverage gaps in the current ground-based array. Space-based telescopes avoid atmospheric turbulence and could observe at shorter wavelengths where resolution improves proportionally. The goal is to achieve angular resolution fine enough to see the photon ring, a bright, narrow ring of light from photons that orbit the black hole one or more times before escaping. The photon ring carries a sharper imprint of the spacetime geometry than the broader emission from the accretion disk and provides cleaner tests of general relativity. Detecting and characterizing the photon ring requires resolution about 5 times better than the current Event Horizon Telescope, achievable with orbital elements or shorter wavelengths. Time Domain Event Horizon Telescope. Observations will track how the image changes with time, revealing the dynamics of the accretion flow as hotspots or instabilities orbit the black hole. Combining this with simultaneous X-ray, optical, and radio observations at lower resolution will connect the horizon-scale physics to the larger-scale accretion, flow, and jet, building comprehensive models of how black holes accrete and launch outflows. Polarization measurements, already being done by the Event Horizon Telescope, map magnetic field structure around the horizon by measuring how the electric field of light waves is oriented. Synchrotron emission from the accretion disk is polarized, perpendicular to the local magnetic field direction, so polarization maps reveal field geometry. The first polarization images of M87's black hole showed an ordered field structure consistent with models where magnetic fields play a crucial role in accretion and jet launching. Future polarization observations at higher resolution and time resolution will test magnetohydrodynamic simulations and constrain field strengths and geometries that cannot be measured by other means. LISA, scheduled to launch in the mid-2030s, will observe gravitational waves from supermassive black hole mergers across cosmic history. The mission consists of 3 spacecraft flying in formation 2.5 million kilometers apart, forming a giant laser interferometer in space. LISA will detect mergers of million to billion solar mass black holes out to redshifts beyond 10, potentially seeing black holes formed from the very first generation of stars. The gravitational wave signals will reveal black hole masses and spins with percent-level precision and test general relativity in the strong field regime. LISA will also observe extreme mass ratio inspirals, where stellar mass compact objects spiral into supermassive black holes, producing thousands of orbits over months to years before the final plunge. These signals map the space-time geometry around the supermassive black hole in exquisite detail, measuring deviations from the Kerr metric at the part per thousand level. LISA will additionally detect galactic binaries, white dwarf binaries in our own galaxy, that emit gravitational waves at millihertz frequencies, and create a foreground that LISA must characterize and subtract to see extragalactic sources. The Einstein Telescope and Cosmic Explorer, proposed next-generation ground-based gravitational wave detectors, will have 10 times better sensitivity than LIGO, enabling detection of stellar mass black hole mergers out to redshift 10 or beyond. These facilities will observe thousands of mergers per year, mapping the black hole mass function and merger rate across cosmic history. They will detect the first black holes formed from population 3 stars, revealing whether these first-generation stars collapsed into black holes and what mass range they occupied. They will also probe the intermediate mass black hole range more thoroughly, detecting mergers involving black holes from hundreds to tens of thousands of solar masses that are rare enough to evade LIGO but should be common in Cosmic Explorer's larger volume. AXIS, the Advanced X-ray Imaging Satellite, proposed for the 2030s, will combine the angular resolution of Chandra with the collecting area of XMM Newton, providing major improvements in X-ray observations of black hole accretion. AXIS will resolve accretion disks in nearby active galactic nuclei, measuring temperature and density profiles that test disk models. It will detect faint X-ray binaries in external galaxies, building larger samples for population studies. It will observe tidal disruption events in their early phases, catching the initial shocks and disk formation. AXIS will perform time-domain observations of black hole variability on timescales from milliseconds to years, probing different physical processes across this temporal range. The Extremely Large Telescope, Giant Magellan Telescope, and 30-meter telescope, ground-based optical, infrared telescopes with primary mirrors 25 to 39 meters in diameter, will achieve angular resolution, rivaling space telescopes in the infrared, where adaptive optics can correct atmospheric turbulence. These facilities will observe stars orbiting Sagittarius A*, tracking their orbits with such precision that deviations from Keplerian motion due to general relativistic effects, become measurable. They will detect fainter stars closer to the black hole where relativistic effects are stronger. They will measure the orbits of stars around supermassive black holes in nearby galaxies, determining black hole masses and potentially detecting binary black holes through their gravitational influence on stellar orbits. The combination of these future facilities across electromagnetic and gravitational wavebands will create a comprehensive picture of black hole physics from formation through growth to final merger. Multi-messenger observations combining gravitational waves, electromagnetic radiation, and possibly neutrinos from the same events will reveal how black holes interact with their environments and test general relativity across a range of field strengths and dynamical regimes. The philosophical implications of black holes extend beyond physics into questions about the nature of reality, knowledge, and existence. Event horizons create absolute boundaries beyond which we can never retrieve information, establishing fundamental limits on what we can know about the universe. This limitation is not technological but rooted in the structure of space-time itself. No conceivable advance in instrumentation can reveal what lies inside a black hole's event horizon to an external observer. This forces us to accept that some aspects of reality are necessarily hidden from view, challenging the Enlightenment ideal that all of nature can eventually be understood through sufficient investigation. The existence of singularities where physical quantities become infinite and our equations break down suggests that our current framework of physics is incomplete. General relativity predicts its own failure at singularities, pointing toward a deeper theory we have not yet discovered. Quantum mechanics might resolve singularities, but merging quantum mechanics with general relativity has proven extraordinarily difficult despite a century of effort. The stubbornness of the problem hints that we might need genuinely new concepts rather than just technical improvements to existing theories. Black holes force confrontation with these limitations and drive the search for better understanding. The information paradox raises questions about whether information is truly conserved at a fundamental level or whether black holes represent true information sinks where quantum information is irretrievably destroyed. If information is conserved as quantum mechanics requires, then it must be encoded in Hawking radiation through correlations too subtle for Hawking's original calculation to capture. Unraveling how information escapes requires understanding quantum gravity at the horizon scale, a problem that has occupied theoretical physics for decades and remains incompletely solved. Alternative resolutions involve even more radical ideas like information being transferred to other universes through the singularity, or remaining frozen at the horizon in ways that don't quite create the firewalls that would incinerate infalling observers, yet somehow satisfy quantum unitarity. The proliferation of proposed resolutions reflects our uncertainty about which principles to trust when quantum mechanics and general relativity make seemingly incompatible demands. Black holes also connect to questions about the arrow of time and the origin of entropy. The second law of thermodynamics states that entropy always increases, creating an arrow of time pointing from low entropy past to high entropy future. But the microscopic laws of physics are time-symmetric, operating the same whether time runs forward or backward. The entropy increase emerges from statistical properties of systems with many degrees of freedom rather than from fundamental asymmetry in physical law. Black holes have enormous entropy, and black hole formation irreversibly increases the total entropy of the universe. A star that collapses into a black hole creates vastly more entropy than existed in the original star because the perv c, the black hole's horizon area entropy, dwarfs any entropy the stellar material previously had. This makes black holes the ultimate entropy generators, driving the universe toward heat death more efficiently than any other process. When black holes eventually evaporate through Hawking radiation, their entropy is transferred to thermal radiation that disperses into the expanding universe, maintaining the entropy increase. The fact that black holes both create enormous entropy when forming and respect the second law throughout their evolution connects gravity to thermodynamics in ways we still do not fully understand. Some physicists propose that space-time itself might emerge from more fundamental quantum information structures, where entropy and information play primary roles while geometry is derived. In such frameworks, black holes would not be objects in spacetime, but rather special configurations of the underlying quantum information that happen to look like geometric objects when viewed at large scales. The holographic principle and ADS, CFT duality, support this view by showing that physics in a gravitational spacetime can be equivalently described by a quantum theory without gravity living on the boundary of that spacetime. If spacetime is emergent rather than fundamental, then understanding how it emerges from quantum information might resolve the information paradox and singularity problems naturally, since these problems assume spacetime is fundamental when it might not be. These ideas remain highly speculative and mathematically challenging to develop, but they represent potentially revolutionary shifts in how we think about reality itself. The journey into black holes has taken us from historical predictions to modern observations to future prospects to philosophical implications. We have explored the event horizon where space and time exchange roles. We have examined the singularity where our theories break down. We have studied Hawking radiation and its challenge to information conservation. We have observed gravitational waves from merging black holes and photographed the shadow cast by a supermassive black hole's event horizon. We have traced how black holes form from dying stars and from mysterious processes in the early universe. We have investigated how they grow through accretion and mergers to become the supermassive monsters ruling galactic centers. We have seen how jets and feedback from black holes influence galaxy evolution across cosmic history. We have discussed alternatives to black holes and why observations favor the black hole interpretation. We have looked ahead to future facilities that will test general relativity with unprecedented precision and map the black hole population across the observable universe. The universe contains black holes at every scale, from stellar masses to billions of suns. They populate galaxies, drive quasars, shape galaxy clusters, and might constitute dark matter. They defy intuition yet obey precise mathematical laws. They hide singularities behind event horizons yet remain observable through their interactions with surrounding matter. They represent gravity's ultimate victory over all other forces, yet eventually evaporate through quantum processes. They are both the simplest objects in astrophysics, characterized by only 3 parameters, and the most complex, connecting quantum mechanics, general relativity, thermodynamics, and information theory in ways we are only beginning to understand. Studying black holes pushes physics to its limits and beyond, exposing gaps in our knowledge and driving progress toward deeper understanding. They serve as laboratories for extreme physics, where gravitational fields reach maximum possible intensities and space-time curvature becomes severe. They challenge our assumptions about what is knowable and what is real. They force us to confront the incompleteness of our current theories and search for better ones. They inspire wonder at days, nature's extremes, and determination to comprehend them despite the difficulties. From Michel's prescient speculation in 1783, to Einstein's reluctant prediction in 1915, to Schwarzschild's exact solution in 1916, to Oppenheimer's collapse calculations in 1939, to Hawking's radiation discovery in 1974, to LIGO's gravitational wave detections beginning in 2015, to the Event Horizon Telescope's images starting in 2019, the black hole story spans centuries and involves some of humanity's greatest intellectual achievements. The journey continues with new observations, revealing new phenomena and new theories proposing new explanations. The abyss looks back at us across the gulf of space-time, challenging us to understand what lies within. We have come remarkably far from darkness and ignorance toward knowledge and understanding. We can now photograph black holes, detect their mergers, measure their spins, map their surroundings, and test the theories that predict their properties. Yet fundamental questions remain unanswered, mysteries persist at the frontier of knowledge, and the deepest secrets of singularities and quantum gravity continue to elude us. The journey into the abyss is not complete and may never be complete, but each step forward reveals new wonders and deepens our understanding of the cosmos and our place within it. Black holes exist, they are real, they are spectacular, and they are waiting in the darkness to teach us truths about reality that we cannot learn any other way.